Good day everybody. In this video I will explain how we can estimate the stability of rock wedge, which is shown here schematically. And we're going to look at the planar failure. In this case we have rock mass, and it might go down because of the weight of the rock mass. So that will be the weight of that wedge acting downward. And we would like to know how stable it is. So it will be a little bit long video with lots of calculations. I will start with explaining this diagram and what forces acting on the rock wedge. And then we're going to look at the formulas, and at the end of the video we're going to go through a few cases. We'll include seismicity, water, and reinforcement. So first let's see what forces acting on the rock wedge. So as I already said, that will be the weight of the rock mass, and we can estimate, it's shown here. So this is the formula to estimate the weight of the rock wedge. And in this example, we're going to look at the special case when we have a tension crack here. So here at the back, behind the crest. And we also know the depth of this tension crack. If we don't know it, we can also estimate using this formula, and I will show you later how to do that. What we also need to know is the failure plane angle. So in this case, it's going to be alpha. So this is going to be the failure plane. And we also need to know the length of this failure plane, which is going to be this one, A. So this one we use in meters. What we also would like to know is the angle of the slope face, which is beta. So that will be the angle. So we're going to use this in calculations as well. Few more things is that if we have groundwater, we would like to know the effect of groundwater on the base of the edge here. That will be U. And if we also have a tension crack and there is water filled in the tension crack, there will be additional force acting horizontally. That will be V. If we would like to think about how to stabilize it, and if we would like to use anchors, so we can also estimate anchors, the effect of anchor on the stability. In this case, we would like to know this value of T, which is the anchor force, and usually we can design it. And we also would like to know the inclination at which we're going to install the anchor, which is going to be theta, anchor's angle. Okay, so to estimate the stability of this rock wedge, we're going to use a safety factor. The idea of the safety factor is we're going to compare driving forces. So driving forces because of the gravity and because of the inclination, alpha. And resistance forces, forces that actually will keep it stable. And this will come from the strength of the rock mass. In order to characterize the strength of the rock mass, we would use cohesion. So this will be cohesion, and that will be the friction angle of the rock. So these are the values here. So these values typically come from either side on laboratory investigation, and we know that one. Or if we don't know, we can get some estimation. So that will be the general idea of the safety factor. And now when we apply it to this particular case, when we have a tension crack, the safety factor will be calculated using this long formula. So this formula includes everything. So it includes the strength of the rock mass. You see here we have cohesion, and here we have friction angle. It will also include seismic coefficient, this one. So this is the seismic coefficient that would come if there is any shaking, like earthquake, right? So then we have two values that are related to pore water pressure. So this value U, which comes here, that's at the base of the wedge, the uplift force of the water. It's shown here. And another value related to pore water pressure is V. So V comes from that horizontal driving force that will try to drive the rock mass down. It also comes from pore water pressure. So you see that U and V, they're on both on the top and the bottom. So at the top, we actually subtracted because polar pressure would reduce the strength of the rock mass. And here you see that we have at the bottom is because it will actually increase the driving force. It will actually add that additional component to drive that rock mass downward. Here we also, you can see this T, so that will come from the anchor. In this case, you see it's also on the top and the bottom. On the top, because it's going to add to the strength of the rock mass. And here at the bottom, it's because it's going to decrease the driving force acting on this rock wedge. Okay, now let's look at the example. Let's say that we have these characteristics of the rock mass. So you see that the height of the slope is 12 meters. So the inclination of the failure plane is 35 degrees. The angle of the slope face is 60 degrees. We also know characteristics of the rock mass. Average unit weight is 26 kilonewton per cubic meters. And we also know friction angle of the rock mass 37 and cohesion, not very high, but it's 25 kPa. What we also know, and it's known already, that unit weight of water, it's 9.81 kilonewton per cubic meters. And here is given that the depth of the tension crack, so this is Z, so here is 4.35, but I will show you that we can actually estimate it using the formula. So what I will do first, I will show you how we can get this value Z, depth of the tension crack. Then we'll estimate value A, which is the length of the failure plane. And then we're going to estimate the weight of this rock mass. And after that, we'll look at a few different cases when we have a dry slope, we have polar pressure, we have seismic coefficient and anchor. Okay, so let's start with value of Z. So in this case, value of Z, we're going to use the formula, which is here, is going to be 12, which is h, which is at the height of the slope, times 1 minus, this will be square root of cotangent of the angle of the slope, which is given as 60 degrees, and times on the tangent of the failure plane angle, which is 35 degrees. So if we estimate it, it's going to give us a value of around 4.35. If we round it up, it will be 4.35 meters. So that's what we get it. So basically, you actually don't need to know the depth of the tension crack in this example, because you can estimate it based on the geometry of this rock mass. You just need to know this angle of the slope face and the angle of the failure plane. Okay, so now let's go with this value A. A is the base of this wedge of the rock mass. It's given as h minus z, which is, let me look at my notes, is going to be 12 minus 4.35 meters, and divided by the sine of the failure plane angle, which is 35 degrees. That will give approximately 13.34 meters. So why do we need to know that? It's because we are going to apply the cohesion here. You see, that's very important. The cohesion of the rock mass is acting along this failure plane, so along the whole 13.34 meters. Okay, so now we're going to estimate the weight of this rock mass. This is a really big formula. I'm going to write it down here. So weight will be unit weight 26 times height of the slope, it's 12 in the power of 2 divided by 2. Then we have here 1 minus. Here we have the ratio of the crack length, which is 4.35, divided by the height of the slope 12 in the power of 2. And here we have times cotangent alpha, which is 35 degrees, and minus cotangent beta, which is the slope angle, and it's 60 degrees. According to my calculations, it will be 1,241.4 kilonewtons per meter. So because we assume that the width of this rock wedge is 1 meter, so that's why we have 1,241.4, and the units are kilonewtons divided by meters. Okay, so now let's go to the next slide. In this case, we're going to use this value where they calculate it, and we see how we can apply to different cases. Okay, so this is what we already know. So these are the values that I just estimated with you guys. And next one, okay, so this one was given. It's exactly the same. I just copied it from the previous slide. And now we're going to look at 4 different cases. So the first case, we're going to look that there is no water. So there is no water pressure. So it's a dry slope, and we're going to estimate the safety factor. So we're going, for each of the case, we're going to use this formula. But for some of the cases, some components in this formula are not going to be there. So we just be mindful of that. So for the first case, we have dry slope. There is no water pressure, no seismicity, and no anchors. So we're going to use cohesion, which is 25 kPa, times A, which we already know it's 13.34. Then we're going to put plus. Weight of the rock mass is 1,241.4 times. Here we have cosine of the angle of 35 degrees, which is the inclination of the failure plane, is this one. And here we have minus seismic coefficient, but in this case we don't assume any seismicity, so we're going to put 0. It's going to be 0, right? So these values of U and V, there is no water pressure, so it's going to be minus 0, minus again 0 for water pressure, then plus 0 because we don't have any anchors force. And in the end, we are going to multiply it by the tangent of the friction angle of the rock mass, which is given as 37. Tangent 37 degrees. Okay, now we're going to divide it by the, here we have again weight of the rock mass, which is 1,241.4 times, here we have sine of 35 degrees. Again, we have no seismicity, put 0 here, and no water pressure, V is equal to 0 because no water, 0, minus there is no force, any action from the anchor, 0, right? So you see all these values are 0. So according to my calculation, safety factor is going to be 1.54. If you know this one, safety factor more than 1 means that slope is stable. If it's less than 1, it means that slope is in critical conditions, and well, it's not in critical conditions, it's considered unstable. Okay, so that was the first case. So now let's see, for example, if we have lots of rainfall and all this water from the surface, from the rain, will go inside this rock mass, and it will generate water pressure. So we're going to look at the worst case scenario when we have water in the tension crack. So we have water here, and we have its water the same height of water in tension crack as the whole tension crack. So in this case, it says 100%. So this means that tension crack is 100% filled with water. And of course, water will be at the base of the this rock mass, and we're going to estimate values of U and V, and then we'll see how it's going to change the safety factor, right? So we're going to start with the value of U. So this is the uplift force acting on the base of the rock wedge. So it calculates by unit weight of water 9.81 times the depth, the thickness of the depth of water in the tension crack, which is the same as the length of the tension crack, 4.35. This is just the assumption that we made, right? So if you have a different value of water in the tension crack, then you're going to put a different value here. And then we're going to multiply it by the whole length of the base of the rock wedge, 13.34, and divided by 2. So this we're going to give us value of 284.6, right, kPa. So it's going to be already water pressure, right, because we multiply it by this value of 9.81. It's not force anymore. Okay, now let's look at this value V, which is horizontal driving force due to water pressure water in the tension crack. So V will be equal to unit weight of water, 9.81, times here we have the amount of water in the crack, and we know it's the whole length of the crack in the power of 2 divided by 2. That will give us a value of 92.81 kPa. Okay, so now we're going to estimate the safety factor for this second case when we have water, and we see if it's going to be different from the case number 1 when we have no water. So I'm going to write it down here. Safety factor is equal. Again, we start with what we know. We know that it's still the same cohesion, 25 times value 13.34. Then plus here we have the weight. It's we know it's 1241.4 times cosine of 35 degrees. So we still have no seismicity, so it will be 0, right? But now we have water pressure. We're going to subtract the value of U, which is 284.6. Then we're going to subtract value of V, which is 92.81 multiplied by sine of 35 degrees, which is the inclination. We have inclination of the failure plane. We have no T, there is no anchors yet, so that will be 0. And then we're going to multiply it by tangent of the friction angle, which is 37 degrees. My pen is not right. Okay, 37 degrees. Okay, and this one we're going to divide by what we have. So we have again W, which is 1241.4 times sine of 35 degrees. Again, there is no seismicity, so it will be, that value will be 0. But we have that value V, which is water pressure, 92.81 times cosine of 35 degrees. And again, we don't have anchor yet, so in this case will be 0. Value T will be 0. So if we do some calculations, and I did it beforehand, the value of safety factor will be 1.07. You see that when there is water pressure, of course, the stability of the rock mass would decrease. And before it was 1.54, it became 1.007. Okay, so now what we do is we're going to consider also effect of earthquakes. So to consider effect of earthquakes, we're going to use the seismic coefficient, which is 0.08 G. So this seismic coefficient depends on the area that you work with. In some areas, some countries, there are like no earthquakes at all. So in this case, this seismic coefficient would be close to 0. In some countries, let's say Japan, New Zealand, US, China, when there are earthquakes, so in this case, this coefficient can be greater. So you need to do some research to find out what the seismic coefficient in the standard, in the design standard for the area you work with. So for the sake of this example, we're going to use value of 0.08. And let's see how it's going to change everything, if it's actually going to change anything. So in this case, for case 3, let's estimate safety factor. So in this case, again, the first component, which is cohesion times A, will be the same, right? Then we are going to have plus, here we have W, which is 41.4 times, here we're going to have cosine of the angle, we're going to fairly plane angle, which is 35 degrees. And here we have additional component that comes from seismicity. It will be 0.08 times on multiplied by sine of 35 degrees. Then the rest is the same as in the previous case. We have value of U, which is 284.6. Then we subtract even more water pressure, which is 92.81 times sine 35 degrees. Still, there is no reinforcement, so the value of T is equal to 0. Multiply by the tangent of the friction angle, which is 37 degrees. And this everything will be divided by W 1241.4 times sine of 35 degrees. Here we have seismicity, so we're going to add seismicity 0.08 times cosine of 35 degrees. We also have this value of V, which is 92.81 times cosine of 35 degrees. And that's it, because T is still 0. So according to my calculations, the safety factor will be 0.92. Okay. This means that you see when there's water in the cracks and at the base of the rock mass, and if we consider also some seismic shaking from potential earthquake, the stability of this slope becomes less than, the safety factor becomes less than 1, which means that this actually rock wedge, rock mass can become unstable during earthquake. Right, so this is what we need to consider. And look at the case number 4. Okay, so it will be the same as case number 3, but we are gonna actually try to reinforce this rock wedge. So we will try to increase the safety factor. So we're gonna apply this anchor here in the rock mass, and then this anchor will add 400 kilonewton of force. We try to make it stable, the rock wedge, and we're gonna put it at the angle theta of 55 degrees. Okay, so now let's see what is going to happen to the safety factor, if it's going to change or not. Let's estimate, I'm going to put it here, safety factor. So basically everything will be the same. We're just going to add the last component T here. So this will be the same. So 1241.4 times cosine of 35 degrees minus this seismic coefficient 0.08 times sine of 35 degrees minus u, which is 284.6, then minus v, which is 92.81 times sine of 35 degrees. Okay, here there will be additional force that comes from the anchor. So we're gonna put here at 400 force, and then we're gonna multiply by sine of here we have theta plus alpha, which is 55 plus 35 degrees, and everything will be multiplied by tangent of 37 degrees because that's the friction angle. This one we are gonna divide by again almost the same thing as in the previous example, but we're gonna add also the value of t. Here we have sine 35 plus this seismic coefficient 0.8 times cosine of 35 degrees. Here we have that water pressure component 92.81 times cosine of 35 degrees. And here comes, we're going to subtract from the driving forces this 400 times on cosine of, again, 55 plus 35 degrees, right? Okay, so there is no space on the slide. I'm going to write here. I did the calculation before, and then it was safety factor will be 1.80. So you see that safety factor is actually increased by almost double compared to case number 3 because of this anchor that we installed in the rock mass, right? So with the anchors, it also depends at what angle you're going to install it. So if you have a more steep or gentle angle, that will also decrease or increase the safety factor. And also depends on what force you're going to apply, because this is a tension anchor, so what force you apply. In this case, we use 400. You can apply less and see if safety factor will be still above 1 and slope will be stable or not. So this is for you to decide when you do design what exactly you would like to do, what safety factor you're aiming at, and also in terms of the cost of the work, so how expensive or like cheaper that will be. Okay, thanks for watching this video. I hope now you know how to do slope safety analysis for planar failure. Have a nice day. Bye.